Hello everyone, this is our group project and today we will be presenting our Bluetooth controlled car with automated object detection. My name is Connor McIntyre and I served as the group leader for the project. Joining me today in our presentation is our hardware specialist Victor Granado and our software specialist Denny Orellana, who we will be hearing from later on in our presentation.
We wanted to do this project because of our shared interest in the practical application of Bluetooth and sensor detection technology. We were eager to explore how these two principles could be integrated in a car. Our primary goals for this project was to create a car that could be manually controlled via Bluetooth, with the included safety feature to automatically stop when its sensor detects an object to prevent collisions. Our second goal was to implement an autonomous mode, allowing the car to navigate a path while independently avoiding obstacles. In our presentation today, we will provide an overview of both the hardware and software components of the car, explaining how each part contributed to the overall design and functionality of our car. We will also provide a demonstration to showcase its operation and highlight its key functions. Following the demonstration, we will conclude by discussing the difficulties we encountered, the key lessons we learned, and the potential features we envision for the future iterations of this project.
Next, we will have Victor talk about the hardware components for our project.
Hello everyone, I'm gonna go into the hardware section of the project. We decided to go with the Lego smart car frame. Um, um, to discuss a little bit of our goals, we wanted to have the Bluetooth remote and the app UI on the smartphone. In addition to the obstacle avoidance, you're also gonna have the wall follow mode, where the car scans 180 degrees to find a wall and then maintains a 20 centimeters gap with that wall. And also have the 2D mapping and logging of the data sent to the app. So going to the components, on the body we have the microcontroller. It's an Arduino Uno R3. For the power, we have two battery cells. Each one's 3.7, so we have a total of 7.4 volts nominal, which powers the DC motors and everything else. It powers the DC motors using the L298N driver. The driver motors, we're gonna use 4 of them. So it's 4 6 volts gear motors for the differential steering. And for the sensors and communication, we're using the HC-SR04 ultrasonic sensor and the SG90 servo for orienting the the ultrasonic sensor. We're also using a 3-channel IR tracker. We're not particularly implementing that into this project, but it's available. And we are using the HC05 Bluetooth for communicating through the app. And then going more in depth over the components here. The Arduino Uno is gonna use 5 volts. It's onboard 5 volt regulator. The motor driver is gonna use 7.4 to 8.4 volts, and that's coming from the battery. The DC drive motors, they're gonna use 6 volts, as I said before. The servo motor SG90, which has the ultrasonic mounted on it, it's using 5 volts, drawing up to 250 milliamps. The ultrasonic sensor itself is also using 5 volts for the trigger and echo. The Bluetooth module, it's using 3.3 volts for transmission receiving. And the battery charger module, which is just used to charge the batteries, it's USB 5 volts as well. I also want to explain the hardware diagram block, so how we decided to go over this. We have the Arduino Uno board connected to the PWM driver on top. You can see that on the Lego frame, and that is connected with the Bluetooth module and the IR receiver. With the Bluetooth module, we accomplished the app communication for both apps for controlling the robot and also getting the data from the 2D mapping. And then from that driver, we connect the other driver which drives the DC motors. We have 4 of them. They all use 6 volts, so it's quite a lot, but we managed to do that with the driver. And then from the same driver, we're using I2C communication, and with the ultrasonic sensor that's getting the data. It's used for the 2D mapping, the coordinates, and also the object detection. Some of the challenges I had for hardware are noise and jitter. So a single ultrasonic reading can jump around, and we solved that using the 5 sample moving average. I also struggled with the blocking delay. The early code used delay, which froze the loop, and we refactored to non-blocking timing with the millis. Another challenge we faced was the mode switching, and we needed to ensure the instant exit from the wall follow mode, and also the tuning of the P gain. If it is too low, it becomes sluggish, and if it is too high, you have oscillation. And we ended up on a KP equal to 2 and a deadband plus or minus 5 centimeters. So this is the demo for the wall follow function. I'm mapping the function to this button right here, and it should scan 180 degrees, look for the closest wall, and start following the perpendicular with the minimal distance threshold. So here we go.
So I will be talking about the software design. For this project, we were using C++ as our coding language for its combination of low-level hardware control and the object-oriented structure, which helped us manage our code better and make the process of debugging and finding errors easier. The robot operates with several different modes. It supports control via IR remote and Bluetooth. It also has a few autonomous functions, which include obstacle avoidance, wall following, and 2D mapping, which is meant to build a map relative to the robot's starting position. Line tracking was also developed, but later omitted from the final version because we had to prioritize the features that we needed to develop ourselves, and due to timing and resource constraints, we just couldn't follow up with it. The software architecture is a super loop that functions as a state machine. It uses global variables to track the active mode and switch statements to execute the code that is relevant to that active mode. This design is to help manage the robot command and prevent conflicting operations to ensure stable behavior and so that the car runs as we want it to. We used a superloop architecture instead of a real-time operating system, or ROTS, because we needed simplicity and we needed to ensure that we wouldn't be running into memory issues with our Arduino. There was advantages and disadvantages to this. For starters, the advantages was that it was easier to implement because it was simpler, and debugging also was made more simple. It doesn't use as much memory, which was good for our microcontroller. But also, we realized that a super loop is inflexible because the tasks run sequentially, which means that there is um, increased response times. But for our applications, the processing loop was fast enough so that um, the command inputs and all the sensor inputs would run without noticeable lag by the user, which made it the correct choice for our goals in this project. And the block diagram shows how our program flows. It's illustrates the startup sequence, how we go through. We start at the main part of in the main loop, and the internal logic of each of the modules that we use. Everything runs inside the main loop, which begins each cycle by pulling for new commands from IR and Bluetooth receivers, and then simple movement commands are processed immediately, um, handling direct remote, handling the direct remote control functions. Mode switching commands are routed to the mode switch block, which acts as our state machine, um, activating the corresponding modes such as obstacle avoidance or wall following. After we do take any action on the car, the update odometry function is called to recalculate the robot's position relative to where it started. And this will also be used for our 2D mapping feature to ensure we always have an up-to-date location estimate for our map. So in summary, this diagram will thus show how our super loop architecture polls for an input, uses the state machine to select the mode of operation, and executes the necessary functions to carry out the command in a stable and repeating cycle. And for our 2D mapping and odometry logic, um, this the process of mapping that we use is called odometry, which is estimating the robot's position over time based on the movement that that the car has made. The core logic is handled by two key functions, which are update odometry and send coordinates over Bluetooth. So the track motion, the update odometry function is called constantly in our main loop, and it checks how much time has passed since its last update and what the car's motion is, if it's going forward, if it's going left, right, or if it's stopped. We also have recalibrated constants in the code, such as centimeters per millisecond forward, back, or such values, and these are the best estimates that we have seen for how many centimeters the car moves or how many degrees it turns every millisecond that the motors are active. And ensuring that these values are correct is one of the main things we have to do in order to ensure that the accuracy of our 2D mapping. And so to calculate any position, we use basic trigonometry. The function updates the robot's current x and current y coordinates. And then if the car moves forward, it adds the distance traveled along the current heading. If it turns, then it updates the heading angle relative to the heading that it had when it started. Then the send coordinates over Bluetooth function runs whenever mapping is active, which can be toggled either by the app or the IR remote using the pound key. Every 9 seconds, it bundles the latest coordinates and heading into a formatted string and sends it over Bluetooth to an app on our phone that can then plot these points and show us on our screen to visualize the robot's path.
We actually had a design prior to our car that didn't end up working, and this was our spider robot. As cool as the idea was, and with how passionate we were to make it work, there were way too many complex problems to tackle with our manpower and allotted time at this point in our project. The main problem with the spider design is that we needed to program in a third movement axis so the robot could properly move. We could have the legs move side to side and up and down. The major part we were missing was a way for the legs to extend forward. Our servos at the time did not support this third axis. After some research, we discovered that the servo needed would already be pricey. Factoring this in for each leg, and not only would it have taken much more time to replace the servos, it would also have cost a lot more money to get the servos replaced. Another problem we found was in the spider robot and the sensors. Seeing as the spider had a much more complex movement pattern and the fact that each leg needed to be considered in object detection, there would have been an extensive amount of testing and troubleshooting to make the design work. With all these factors to consider, we decided as a group it would be best to have a redesign to the car.
So, in conclusion, at least for the hardware part, um, we can see that the wall follow function works pretty well as intended. Uh, there were some minor fixes that had to be made, but I think it accomplishes what we expected from this. Some things, some takeaways that I got is how to integrate the hardware, like the motors, the servos, ultrasonic sensor, the Bluetooth, with the software, the code, as in the state machines, the non-blocking code, and the P control. And also the importance of sensor filtering and the timing. That is very important for the performance of the robot in general.
And for me, one of the things that working on this project helped me to see kind of a real life application is that there's always going to be some kind of problem or something that you don't account for. Specifically for our project, we were in the last stage of the wall mapping or the mapping function. And the controllers were not working, like the movement controls weren't working because it was updating the mapping way too often, and so that was filling up all of the memory, and it wasn't able to write any move commands. So my takeaway is just like there's always going to be like unforeseen problems, but just be willing to be a little patient, ask for help from teammates and from look up similar issues on the internet, and just always find like creative ways to move forward and brainstorm with other people.
And I would also like to conclude a couple of the more general takeaways that we got as a group was, again, and primarily when we learned how to work in a group, we learned how to better time manage. There was a situation, again, where we lost a team member, so we learned how to work with less team members, or just whenever a shortcoming might happen, we learned how to improvise and also work around and plan around those shortcomings. For our project, a couple of the main ideas we learned was Bluetooth modules on microcontrollers, and also how to design and select components for a project. And then just some things we want to implement for the future, just for our car. We want to increase the complexity of the automated path finding. So just add more routes, more different scenarios where it can work. We also want to maybe add an adjustable height for the robot. So if it needs to go under someplace lower or higher, it can adjust the height automatically. And then for the battery level, we want to include that on our UI. And also we want to add an option on the Bluetooth controller for a horn, just for it to honk if it needs to. And that concludes our project. Thank you for listening, for watching,